Here's a real problem. A long line carries power to a town far away, but the voltage sags before it arrives. Lights dim, machines strain. A second line costs a fortune. So how do we get more from the line we already have? The answer's a series capacitor, put right in the line. Let's break it down step by step. The thing pushing back is the line's own reactance. Every line has inductance, and the longer it is, the more inductive reactance it has. Call it X. The power you can send depends on the voltage at each end, the angle between them, and that X sitting in the middle. And X is in the denominator, so the bigger it gets, the less power gets through. A long line is basically a long electrical spring. The far end can be at full voltage, but all that reactance in between still chokes the flow. So here's the move. Inductive reactance and capacitive reactance are opposites. They cancel. So we put a capacitor right in series with the line. In the path, the current actually flows through. The capacitor's reactance subtracts from the lines. The line still has all its inductance, but electrically, the current now sees a smaller total reactance. We haven't changed the line. We've canceled part of what was holding it back. And that smaller reactance changes everything. Remember, X was in the denominator. Shrink it, and the same line pushes noticeably more power across, with the same voltages at both ends. The voltage drop along the line eases up too. Engineers describe it with the degree of compensation. How much of the line's reactance the capacitor cancels, usually around 40 to 70%. It's a bit like electrically shortening the line without building a single new tower. There's a second benefit that's just as important, and it's about stability. When something disturbs the grid, a fault, a big load swinging on, the two ends of the line start to pull out of step. What pulls them back together is the power that flows when their angles differ, and a lower reactance means more of that pull. So a series capacitor doesn't just raise how much power the line carries on a calm day. It helps the system stay in step when things get rough. Now you might ask, if canceling some reactance is good, why not cancel all of it? In practice, nobody does. Push the compensation too high, and the line gets twitchy and hard to control, and you run into resonance problems we'll get to in a minute. So engineers leave a healthy margin, taking out a good chunk of the reactance, but never the whole thing. The simplest version is just a big capacitor bank switched into the line, fixed, always doing the same job. But like with the SVC, you can make it adjustable. Put a thyristor-controlled reactor across the capacitor, and you get a TCSC, a thyristor-controlled series capacitor. Now you can dial the compensation up and down on demand, steer how power splits between parallel lines, and actively damp out slow power swings before they grow. Series capacitors do come with one famous catch. A capacitor in the line creates a natural electrical frequency below the normal 50 or 60 Hz. If that lines up with the mechanical twisting modes of a nearby generator shaft, the two can feed each other, and the shaft can actually be damaged. It's called sub-synchronous resonance, and it's the main reason series capacitors are studied so carefully. The good news is, a TCSC can be tuned to avoid it, and every series bank has protection, surge arresters, and a bypass to step in the moment something goes wrong. And just like the STATCOM upgraded the SVC with a converter, there's a converter-based series device too, the SSSC. Instead of a physical capacitor, it uses power electronics to inject a controlled voltage straight into the line, in just the right direction, to act like more or less reactance on command. It's the most flexible of the bunch and the most expensive, so you'll see it where that fine control really earns its keep. So where does this leave us with the SVC and STATCOM? Those are shunt devices. They hang off a bus and manage the voltage at that point. Series compensation works in the line and manages the line's impedance and the power flowing through it. They're solving different problems, and on big systems, you'll often find both: the shunt devices holding the voltages, the series devices opening up the lines. So, to bring it together, A long line is limited by its own reactance. Put a capacitor in series and you cancel part of it, so the line carries more power and the grid holds together better when it's stressed. Keep it fixed for a simple boost. Make it a TCSC when you want control, and watch out for resonance along the way. Shunt devices like the SVC and STATCOM steady the voltage. Series compensation opens up the line. Put them together and you get a lot more out of the grid you already have. If this helped it, click subscribe, and I'll see you in the next one.